I love drinking coffee first thing in the morning. This is my small comforting ritual. What is the first thing you do in the morning? Do you ever start your day by opening your computer to start Spark long-running job before you have had coffee? If you use Spark jobs, you probably work with lots of data, which is exactly what Spark good at. Apache Spark is a unified analytics engine for large-scale data processing. After this talk, you'll have time for a leisurely cup of coffee every morning. Although Spark code is easy to write and read, it doesn't mean that users don't run into issues of long-running, slow-performing jobs. With just a few lines of code, you can get hundreds or thousands of machines immediately working. Which brings me to the second problem, the cost. We will talk how to get the most out of your Spark clusters. By leveraging Spark abilities, it is not uncommon to see the same job running 10 or 100 times faster with the same cluster and the same data. We will take a deeper look on how Spark works under the hood. Spark was designed with an optimizer called Catalyst. The Catalyst optimizer improves the performance of queries by applying rules and evaluating several execution plans. In addition, it allows the Spark community to implement and extend the optimizer with new features. We will put theory into practice by looking into few out of many Spark optimizations and see how the fact that we use UDF influences the performance of Spark. We will compare performance of queries that use Spark functions and queries that use UDFs. User-defined function is a feature of Spark SQL which allows you to extend Spark by adding custom constructs simply by writing your own logic. UDFs come with significant performance overhead compared to Spark native functions, because Spark doesn't know how to optimize UDFs. Spark utilizes the concept of predicate pushdown to optimize your execution plan. The idea of it is that data is being filtered on disk, and as a result, only the relevant data is brought to memory, which saves you I/O and networking. For example, if you specify a filter that only requires to fetch few rows from the data source, the most efficient way to execute this is to access only what is needed. Spark will actually optimize this for you by pushing the filter down automatically. In this example, I've ordered the data by the timestamp field and implemented two queries to filter the data. The first, where I use Spark built-in function to get rows with timestamp greater than some value. The second query does exactly the same, only I wrapped the logic inside an UDF and used the UDF for filtering. From the physical plan that Spark generated, you can see how Spark will execute the query. First, it will scan the data on disk and fetch it to memory. Then, Spark will filter the data in memory. Spark functions query, as you can see in this table, run almost 6 times faster than UDF query. The reason to that is that Spark reads twice times more data when using UDFs. When using UDF, Spark is not able to push down the filters, as it doesn't know the internal logic of the UDF. Thus, it has to read the whole data into memory, and do the logic in memory. This is the reason that the UDF query runs much slower. Here are the pushed filters from the physical plane. You can see the not null standard filters that Spark adds. But in the Spark functions physical plane, we also find additional filter, greater than, which gives us a clue about the logic that Spark will apply to the data on disk, filtering only the relevant rows. In this example, I've partitioned the data by country. And as previously, use Spark function to implement logic that filters USA country. And the same logic wrapped in UDF. In the stage results, you can see that Spark functions query runs 6 times faster than UDF query. The reason to that is the amount of data Spark reads. With Spark function, Spark reads only the relevant partition, while with UDF it has to read all the data and do the filtering in memory. And again, this makes Spark functions much faster. In the partition filters of the physical planes, we find the is not null filters, but in the partition filters of Spark functions, we also find a specific country filter. And as you remember, we partitioned our data by country. Thus, Spark will be able to grab the whole partition without the need to scan the disk or doing additional logic. Constant folding is another optimization that Spark does. Spark recognizing and evaluating constant expressions at compile time rather than computing them at runtime. This is not specific to Catalyst, but it's just standard compilation technique, and its benefit should be obvious. It is better to compute expression once and use the result for each row. In this query, I use 2 fields, start timestamp and end timestamp, in order to filter the data. I wanted to get all the rows that the difference between the end time and start time is less than 24 hours. The timestamps fields were given in milliseconds. The equation speaks for itself. The diff should be smaller than the amount of milliseconds in 24 hours, which is 24 multiplied by 60 minutes, multiplied by 60 seconds, multiplied by 1000 minutes. The very same logic implemented as UDF. And you can see the physical plane. Here all of the filtering done in memory. I wanted to isolate this optimization, so I prevented Spark from optimizing the disk filters. Although Spark reads the same amount of data from disk, you can see that Spark functions are 5 times faster than UDFs. We see that processing time of Spark function is much more efficient than of UDFs. As we said, the optimization happens in memory. From taking a look at the data filters part of the physical planes, we find the standard not null filters that Spark adds. In the physical plane of UDFs, we also can find an obscure filter that doesn't add too much information. But in Spark function plane, we see the logic of our filter with pre-calculated number that equals to the value from the query. Spark substituted the final number by constant value, which he applied in runtime instead of calculating it on each and every row, as UDF query had to do. Let's summarize what we learned here. If possible, not to use UDFs, you better not to. The reason is that Spark cannot optimize the plans when you use UDFs. And as we saw, it can have huge performance cost. Another thing is when your data is partitioned and sorted by the key you use for filtering, this helps Spark to read the relevant data more efficiently. And last thing, when possible, use predicate files to store the data. It has few benefits. First, predicate has schema, which works well with the push-down concepts that we talked earlier. Secondly, there are additional optimizations that Spark can apply on predicate files, such as column pruning, which allows more optimization by reading only the relevant columns. Spark is a huge platform to study, and it has a myriad of nuts and bolts which can optimize your jobs. We covered only few of those nuts and bolts, and there is still a lot to be explored. But before, let's take a moment to sit back, relax, and have your coffee. Thank you for listening. If you have any questions, I'm here to answer, and you can reach out by email or contact me on LinkedIn.